May peace, mercy, and blessings of Allah be upon you. Let we begin our ceremony with the recitation of the Holy Quran by Mr. Muhammad Hanzala.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم والضحى والليل إذا سجى ما ودعك ربك وما قلى وللآخرة خير لك من الأولى ولسوف يعطيك ربك فترضى ألم يجدك يتيما فآوى ووجدك ضالا فهدى ووجدك عائلا فأغنى وأما اليتيم فلا تقهر وأما السائل فلا تنهر وأما بنعمة ربك فحدث صدق الله العظيم.
Now let we rise for the national anthem, please. Honorable Chief Guest of our ceremony, Professor Dr. MSSM, Honorable Keynote Speaker of our today's event, Professor Dr. Asghari Maqsood, dear colleagues, professors, scientists, scholars, and researchers, ladies and gentlemen, Assalamu alaikum and a very good morning. On the behalf of our team from the Department of Physics, Allama Iqbal Open University, I would like to express my sincere gratitude and welcome you to the Conference of Material Science and Smart Materials. Moreover, I honorably welcome our keynote speaker and invited speakers who honored us with their presence in this cold weather from across the country. It is our hope that this conference would be able to achieve its objectives in providing an effective forum of academicians, researchers, and practitioners to advancing knowledge, research, and technology for our society. Dear participants, the focal drive of this conference would be to exchange ideas, and by participating in this exchange, it is hoped that all parties who may benefit from this conference can apply it in managing activities in their areas. It is pleasing to note that the agenda of this conference covers a wide range of interesting topics related to all theoretical and practical aspects of material science and smart materials. Dear audience, let me call upon the chief planner of this conference, Chairman Department of Physics, Professor Dr. Syed Zafar Ilyas, for the introduction and welcome address.
Thank you very much. Assalamu alaikum, respected Chief Guest, Dr. Javed Khurshid Saab, Dr. Asghari Maqsood, invited speakers, and participants. Assalamu alaikum. آج بہت اہم دن ہے. اس کانفرنس کو میڈم کہہ رہی تھی کہ یہ فنڈنگ بھی HEC نے کی ہوئی ہے, یہ میرا پروجیکٹ ہے, اس کے انڈر یہ فنڈنگ ہوئی ہے. تو امپورٹنٹ اس لیے ہے کہ دیٹ از مائی لاسٹ کانفرنس ڈیورنگ مائی ریگولر سروس. So I am going to retire on 27 of this month. So اس لیے بڑی امپورٹنٹ ہے, اور کروائی بھی اسی لیے کہ جاتے جاتے کم سے کم یہ تو بتا جاؤں کہ میں نے یہاں پہ 12 سال میں کیا کچھ کیا. اٹس اے 135th conference of the DIP Department of Physics. We conducted that in the 12 years. اس 12 years میں بھی 2 سال کووڈ کے تھے, تو that what we conducted in the 10 years. جب میں آیا تو we have 3 faculty members. ایک میں تھا, ایک میڈم حریم تھی, اور ایک میڈم سوریا تھی. Now ماشاءاللہ we have 10 faculty members, اور we started the journey with a zero. اور ماشاءاللہ آج کل ہمارے پاس the best lab in undergrad ہے ہمارے پاس. شاید پاکستان میں کسی بھی یونیورسٹی کے پاس ایسی لیب نہیں ہے. ہمارے پاس ریسرچ کی لیبس بہترین لیب ہیں. اس میں سے کچھ اکوپمنٹ پاکستان میں کسی کے پاس نہیں ہے جو ہمارے پاس پڑی ہوئی ہیں. سو دیٹ از وٹ دا جرنی از. اور آج تک ہم سر 600 MPhil پروڈیوس کر چکے ہیں, اور 10 PhD پروڈیوس کر چکے ہیں. ان دا پائپ لائن شاید 25 یا 30 PhDs پائپ لائن میں. تو ہم نے یہ جرنی شروع کی 2009 سے, جب میں نے جوائن کیا, اور 2011 سے ہم نے MPhil شروع کی, اور 2015 سے جب ہماری لیبز بنی تو ہم نے PhD شروع کی. تو یہ وہ ایک جرنی تھی جو فزکس ڈپارٹمنٹ کی ٹیم نے شروع کی, اور فزکس ڈپارٹمنٹ کو اس پوزیشن میں لے کے گئی ہے. اور یہ مٹیریل سائنسز اور اسمارٹ مٹیریل پہ شاید ریگولر سروس میں میری لاسٹ کانفرنس ہے. تو اس لیے بڑی امپورٹنٹ تھی, اور میری خواہش تھی کہ زیادہ سے زیادہ لوگ پارٹیسپینٹ آئیں, اور کافی لوگ آئے ہوئے ہیں, اور مزید آتے جائیں گے. شاید سردی کی وجہ سے دیر ہو رہی ہے, لیکن تھینک یو ویری مچ فار آل آف یو فار کمنگ, attending the conference and presenting your papers. اور انشاءاللہ you will enjoy your stay, اور کوشش کریں گے کہ we will do the best in this conference. Thank you very much to all of you. Thank you Allah.
اب کچھ الفاظ ان کے لیے جو ہماری مہمان ہیں یہاں پر ہماری کانفرنس کے لیے ایک بہت امپورٹنٹ ایسپیکٹ ہیں. ہماری کی نوٹ اسپیکر بھی ہیں. ان سے ہمارا ڈائریکٹ تو کبھی ڈپارٹمنٹ کا اس طرح سے میرا تو کوئی انٹریکشن نہیں رہا, بلکہ بہت سارے لوگ ایسے ہیں جن کا انٹریکشن نہیں رہا, لیکن ہم ہمیشہ جب بھی یہ آتی ہیں ان سے بہت فیض یاب ہوتے ہیں. چلو اب ایسا کرتے ہیں, ستارے بانٹ لیتے ہیں, ضرورت کے مطابق ہم سہارے بانٹ لیتے ہیں. محبت کرنے والوں کی تجارت بھی انوکھی ہے, منافع چھوڑ دیتے ہیں, خسارے بانٹ لیتے ہیں. اگر ملنا نہیں ممکن تو لہروں پر قدم رکھ کر ابھی دریائے الفت کے کنارے بانٹ لیتے ہیں. میری جھولی میں جتنے بھی وفا کے پھول ہیں ان کو اکٹھے بیٹھ کر سارے کے سارے بانٹ لیتے ہیں. محبت کے علاوہ پاس اپنے کچھ نہیں ہے فیض, اسی دولت کو ہم قسمت کے مارے بانٹ لیتے ہیں. پروفیسر ڈاکٹر اصغری مقصود. She is a PhD in Material Sciences from Göteborg University, Sweden. She is currently working as Professor Emeritus, Department of Physics, Air University, Islamabad. She is Sitara Imtiaz. She has her expertise and skills in material science, experimental physics, condensed matter physics, nanotechnology, renewable energy, etc., and having more than 300 publications. Ma'am, please.
Okay, I'm very happy to be here. I always think open university, so this is open for everybody. So whenever I wanted to add something or I wanted to say anything, I came to this department and there was no resistance at all. So everybody, I think, in that physics department, they are friendly with me, and I'm sure I love them and they also want to see me in their department. Okay, so today, uh, according to the nomenclature of the conference, I chose very basic technique for the indexing of the X-ray pattern. Because whenever you prepare a material, we want to make some sort of assessment, and the first thing is that we should go to X-ray diffraction. And now the interesting thing is that in these days, coverage is more important compared to many other things. So we had, okay. So whenever we prepare a material, the most important thing is what is this? So we can only find out the information which is qualitative as well as quantitative with the help of X-ray diffraction. I have dealt with many, many students in centuries now, and in most of the time whenever I go for examination, I find that they have not understood the subject properly, though it is taught in the classroom. But doing something in practice, reading, listening, these are different things. So let's see how we can proceed with this important technique. Okay. Now, the most important thing is X-ray sources. Then we have very important Nobel Prize winner law, which is the diffraction law, and this is after the nomenclature of two person, father and son, and that's known as the Bragg's law. Then we will look into the crystal structure determination, and there are well-known books written on X-ray diffraction. There are chapters written in many books. For example, most of the people, they read and they are familiar with the book Introduction to Solid State Physics by Kittel, and second chapter of Kittel is written on X-ray diffraction, and similarly in many other books over there. So the books which I like to read it, one is the Elements of X-ray Diffraction by Cullity, and another book is which is again written by Elements of X-ray Diffraction. One, Cullity is the same author, some modification is done by Stock. So again, these are two basic important books in the literature, plus many other chapters are available on this. Of course, we should also honor the basic publications which were written almost 75 years ago or 100 years ago related to X-ray diffraction. So the next slide, which is very simple and may be informative, and that is the concept of the electromagnetic radiation. So almost everybody is familiar that with even with a particle, a wave is associated, and with the wave we have electric field and magnetic field that is propagating in the medium, and those fields are perpendicular to. So again, we have given certain nomenclature to this spectrum according to the wavelength or the frequency. So here we can see, for example, we have long radio waves, then microwaves, visible light with which we can see, and we are able to now enjoy the visibility. And then we have got short radio waves, X-rays, gamma rays, and so on. But I am only interested, or we are going to utilize only the pattern or the spectrum, or I should say the wavelength, which lies in the X-rays. Okay. Now these are the simple patterns which are very important, and again we see that we have got 14 Bravais lattices. So there are certain systems, for example, now depending upon how we start, either you can start from the cubic one, or we can go and we look at the triclinic system, and then we can impose certain condition on the triclinic system, that is the lattice constant A, B, C, alpha, beta, gamma. And then accordingly we are able to find out system which are just the 7 system. Now there are only 4 lattices which we consider. The lattices are primitive, base centered, body centered, and face centered. And remember, the only system in which these 4 lattices exist is simply the orthorhombic system. In the rest of the system, we have certain limitation. For example, if I consider cubic, so in cubic, the possibility is either simple, some people also call it as primitive, then body center and face center. It doesn't contain the base centered system. The reason is because in this case only we are dealing with the lattice constant A is equal to B is equal to C, and 3 angles are perpendicular to each other. So if we even consider base centered, of course it will behave like a face centered. Okay, so if I'm trying to put the other possibility in practice, I have got only 14 Brevis lattices in 3 dimension. And if I come and try to put it in terms of 2 dimension, then I am left only with the 5. Okay. Now let's go to the Bragg's law. The idea is simple, and mathematics is also very simple. There is a lot of application. So in this case, the first thing on which we can apply this law is that the material should obey the concept of the single crystal. So how we define a single crystal? That means we must have certain lattice points over there, and then you have to attach the bases to the lattice point. For example, sodium chloride, this is the lattice is simply FCC and basis is sodium chloride. So we can only apply these laws to the concept of the single crystal. Amorphous, we can work with it. And again, there is a certain overlapping of the concept of the amorphous and single crystal. Otherwise, we are not able to apply this law, number 1. Second point is that the incident radiation should be of the order of magnitude of the lattice constant. If the wavelength is higher, then it is not applicable. For example, I am not able to see the structure of a crystal with my naked eyes. The reason is my eyes work only when I am using optical wavelength. And of course, with the optical wavelength, we can't peep through the structure. That means for the structure determination, it is necessary that we should peep with the eyes of the X-rays. Okay, otherwise not possible. Concept is simple. Again, we have simply some planes over there. Right. So here the law is lambda is equal to 2d sine of theta. So here is also written with DHKL. So D means this is the interplanar distance and HKL is the Miller indices, because all the physicists, mostly the physicists are sitting over there, and even the chemists are familiar with the concept of HKL and D, so I'm not going to talk about it. Anyway, so in the figure we can see with black parallel lines, that means we have taken just the planes in a structure, crystal, and then red line, so over there, and it's also given some arrow over there, so beam is incident, it touches with some lattice point, then it scatters, and so on. So just see the parallel beam, and it is also given for simplicity HKL. That means the interplanar distance is connected with the very simple mathematics. Okay, so everything I think I have said already. So the space between the diffracting planes of the atom determines peak position. The peak intensity is determined what atoms are in the direction. So what is meant by peak? That's mean interference, and if we have constructed one, there will be formation of a peak. Otherwise, no intensity will be seen over there. Okay. So here we can just see the concept. And in this diagram, again, you can see that for simplicity, we have taken just two lines. That means two planes interatomic. And here you can see the presence of a smaller atom as well as the bigger one. So it also shows something in which we have just connected the bases to the lattice points. And again, we can have just the diagram which shows the diffraction pattern. Now, how to do the analysis? So, for the determination of the formula, we can see that in the case of the incident line, so if I draw a perpendicular on this line, and similarly, so here we can see some extra distances traveled by this wave as well as this wave, so that here we can have some sort of interference, and detector will simply detect the formation of the peaks or the pattern in which we are interested. In these, in old days, we have different methods of having the formation of the pattern or recording, but in these days it has become very simple that you can simply have a plot on the computer screen and you can see the pattern very easily. Okay. Now, this is just the experimental setup. So another thing which is very interesting, and especially for the students, that see the incident angle is theta, but because of the experimental arrangement, in practice we always measure 2 theta, which is evident from this diagram. And for that reason, when we get a pattern, the pattern is simply 2 theta intensity, and the rest of the job students are supposed to do. Sometime we do, sometime we can also get the information which P correspond to which angle. Okay. And then this is the photograph of the diffractometer, which is normally used in most of the laboratories. And if you remember in your books, it is also written that people use Debye-Scherrer camera. So in the case of the camera, we were recording the pattern on an X-ray film and then reading the distance in between, converted into some sort of angle. But in these days, this picture shows that we have simply X-ray beam, we put a collimator so that we can have only the beam of a single wave. And then we have a sample and we can get the diffraction and then record it. Why we should have a beam of a single wave? Because we have to distinguish whether this corresponds to the structure of the material under consideration or this is just related to the incident beam. For that reason, we have to use a monochromator. Okay. So this is just a pattern which I have chosen from the book, very popular book, Lester. So in this case, we have simply just look at the peaks, and then we have, for example, 1, 1, 0. This is called as the indexing, 2, 0, 0, 2, 1, 1. So how these planes correspond to some particular structure, just look at the structure, and there are a few smart students and they remember this, just looking at the pattern, that this belongs to BCC structure. So just see, this mean 1, 1, 0 mean this peak belongs to this particular plane. Now the same structure, so this belongs to 2, 0, 0, and then this belongs to 2, 1, 1. So just pictorially I am showing that how the peaks are formed according to the structure. Okay, you can have a mixture also, but in that case, of course, the pattern will be rather complicated. So very simple that we can get the peaks, and this correspond to a particular structure. Now, as I said that smart students, I mean, you people are smarter than the student, but the students, they always keep their things in their mind. So I have just now taken a sort of a summary, because in the beginning I said that we can have primitive lattices, body-centered, face-centered, and base-centered. So in this case, we can have the presence of the peaks and the absence of the peak according to the structure also. We can just sit down, do small mathematical calculation, and these small calculations are also done chapter 2 of Kittel, which we teach to our undergrad students also. So over there, if we have a body-centered cubic material, I mean, here I have said cubic, but it's not necessary that it should be only cubic. We can equally apply to other systems also. Then it's necessary that H plus K plus L should be odd number. For example, if we have H plus K plus L is odd, that means we won't be able to see that diffraction line in the pattern. For example, in the previous pattern where I have shown BC structure, over there 1 plus 0 is equal to 2, which is an even number. Or 2 plus 1 is equal to again an even number. If you have an odd number, for example 1, 0, 0, you won't see that peak. Okay. Similarly, look at the face-centered cubic, and in this case the criteria is that either all the HKL should be even or all the HKL should be odd. For example, in FCC, 1, 1 peak is present, 2, 0, 0 peak is present, but you won't see 1, 1, 2 peak, because that will be destructive according to the calculation, and experimentally we don't observe. And similarly, the rest, for example, hexagonal close pack structure, again H plus 2K is equal to 3N, and N is again integer, and here we won't be able to see the presence of the peaks in that HCP structure. Okay. Now I will give you the summary, then I will give you some small examples also. So first thing is, atoms may assemble into crystalline or amorphous structures. Common metallic crystal structures are FCC, BCC, and HCP. You just sit down and you start looking at the periodic table, and then you will see there is only one metal which exists in simple cubic. Okay. Otherwise, you will see either BCC, FCC, or HCP. Why? Because there is a maximum volume which is enclosed by these structure. For example, FCC and HCP 0.74, and if BCC 0.68 or 68%. So these are the stable structure which exist in nature. Then we can predict the density of a material provided we know the atomic weight, atomic radius, and crystal geometry. So you can do the basic calculation, again very simple. Then crystallographic points, direction, and planes are specified in terms of indexing scheme. And crystallographic directions and planes are related to atomic, linear densities, and planar densities. Okay? And normally, what we expect from a material which we should be able to get through the X-ray diffraction, that we can find out the first thing, what is this? You can get what type of structure it is, whether it is cubic, tetragonal, hexagonal, and even you can do the indexing. So with the help of the indexing and the lattice constant, we can get the X-ray density and so on. So we get a lot of information through the X-ray diffraction. Now I said, okay, let me take this sort of a pattern in practice. This is zinc oxide. Students are working in my lab. So now the good thing is, good thing and maybe some sort of a, almost every university has got X-ray diffractometer. And most of the diffractometers are not working. Okay, why? The reason is that we spend a lot of money to buy the equipment, but we don't have people which should be able to mend it. Washing machine is out of order. You simply call a person, the person will come, look at the washing machine, do some sort of a technical things, and then washing machine is ready. Just at the end of the day, maybe 1500 rupees or something, and you are able to use it. But in this case, which is very expensive equipment, we don't have the technical manpower. Something is out of order, now we have to wait. For months and months, we are not able to get the replacement. And in these days, the bigger problem is we don't have the foreign exchange. So even if somebody is interested to help me, they have the problem of getting foreign exchange to get that piece of the purza and just make the replication. So it's very, very difficult, waste of money sometime, I should say. But now just look at the other side, X-ray machines which are being used for the medical science. There are so many laboratories. You go and get it. And I have never heard that X-ray machine is out of order where they are working for medical science. Because those facilities are mostly private. So maybe in future, there should be some sort of a possibility that these machines should be available at different points. A person should go, make the payment, and get the pattern. In practice, what happened, we don't have the technician in our laboratory. A teacher is responsible to do the patterns also. Now, the problem is a teacher has to do a number of the things. For example, teaching 3 courses, supervising few students, okay. So the teacher says, okay, I have trained this student, let this student work for the formation of X-ray pattern. But sometimes, students dil ke badshah hai. They don't bother, okay. And then the result is most of the time machine is not working properly. So in this case, the normal method is, it should be, in my opinion, so we got the pattern, and here you just look at this thing. We get the position, and remember this is 2 theta, as I said previously. In the Bragg's law, we are using theta, but practically we get 2 theta. And then we have got height. Height means this is related to the intensity, counts per second. Then we have full width at half maximum. So with this information, we are able to get the crystallite size and Scherrer formula normally we use. And then we have the d-spacing, and at the end of the day, here relative intensities also. Now, why relative intensity? Because we are making a sort of a comparison, what line with what and so on. So how much is the height? We are just looking at this thing. And maybe I think so in this case, we get the pattern, and this pattern was done by ComSat, Dr. Anisur Rahman. He provided to me. Okay, so these are some geometry. If interested, I will leave the talk. Again, some information to distinguish between the type of the system, HKL and vagara vagara. And of course, then one practical example I will just do, I gave in the classroom to my student. So a Debye-Scherrer pattern of tungsten. Okay. So Debye-Scherrer camera means we have just the record over the X-ray film. Now you have to just take two lines, get the angle, and then we can make the sort of a calculation, how much distance correspond to how much angle, vagara vagara. And then I have written the data is such that line 1, 2, 3, 4, and thetas I have taken only 4 lines. So one very important thing, that if I want to get the exact value for cubic system, how many lines are necessary? At least 4 lines. Why? 1 line, because I have got 4 unknowns, h, k, l, and theta. Okay? So here, if I have taken only 4 lines, then I can get the exact answer. But the good thing is that we should try to have as many lines as possible, though we will get there the most probable values of A. HKL will be, of course, the exact answer. The reason is the condition which is simply imposed on different structures. Okay? So in this case, I have only chosen 4 points, and now we have to put 2d sine theta is equal to lambda, again sine square theta is equal to this much. The reason is simply for cubic system 1 over d squared is equal to h square plus k square plus l squared over a squared. Because theta is known to me, so I have taken theta, wavelength is again known to me, and then I have arrange the equation so that on my right hand side known quantities, on my left hand side A is just a constant, and then we can see if I can choose proper values of h, k, l, then sine square theta over h square plus k square plus l squared should be a constant. So if I choose, let's say, the second line, theta will change, of course, my choice of HKL, and again I should get A is constant. That's mean very good check that all the time I am getting A constant. And then with the help of that, we can also have some thought that how you are choosing the values, as I pointed out already. So if you wish, you can then take average value of A, and from there we can get the lattice constant. So I wrote this plus minus something because in averaging you can get. So by doing very simple calculation, we are able to do it. And remember, in these days, origin programs are available in which you can do these calculations very quickly. Okay. Similarly, I took the same system, I did all the analysis, maybe my time is short, so over there in the case of the zinc oxide, few nice things, you can get A and C. And then you just find out the ratio, C over A. So ideally, C over A is equal to 1.6333. This only exists for helium system, not for the other system. In this case, the interesting thing is for zinc oxide, C over A is equal to 1.02. So 1.60234 something, that means 1.6 is there. So it's a very good system, and we can proceed for further research easily. That means we are very close to the HCP structure. Okay, so this is the case of a quartz. Quartz means is silicon dioxide existing in the form of a single crystal, again HCP. So I did all those analysis. That means we had theta, 2 theta, I got it, converted into theta, sine squared theta, then a squared, 1 over d squared, vagara, vagara, and we are able to find a, kya hai? C is there, yes, fine, okay. And if some person is more interested, then I have shown also working here. Okay, thank you. All right, thank you very much. Questions and discussion is welcome.
Madam, thank you for the nice talk. It was kind of informative and a kind of a revision for us related to these things. Because usually, again, the data and the origin software don't go into the back end of this HTML and all that mathematical equations. Just a question, maybe helpful for the audience as well. Generally, copper is used as a source of X-ray in most of the machines.
See, copper is, I said X-ray sources. So, copper K alpha, this is normally the popular source which our people use, remember. So, in the case of the copper, again, we have got copper K alpha and copper K beta. So, we put nickel as the filter, and what happens over there? The intensity of even copper K alpha. Again, in copper K alpha, we have alpha 1, alpha 2, but we take the average. And K beta is almost eliminated, or maybe very less intensity, and little bit intensity of copper K alpha is eliminated. So that is not the source. I said X-ray sources. Similarly, we can have molybdenum, we can have iron, because we have to take wavelength which is comparable to the lattice constant. So in some cases, copper K alpha is not suitable for if I have got some materials, it may not work. Okay, so copper wavelength, copper K alpha, that corresponding to the copper source. X-ray कैसे produce होती हैं? So you have just some sort of a target, we put some energy over there, so that we get it in practice.
A Pakistani nuclear physicist and professor of physics at the Preston University, who is known for his research publications in understanding the gamma rays burst, Mossbar effect, diffraction, and nanotechnology. He's also known for his neutron science and nanotechnology and nuclear deterrence. The chief guest of our ceremony, Professor Dr. MSSM.
Bismillahirrahmanirrahim. My dear Professor Ilyas, and respected Madam and colleague Khushi, it's a pleasure to be in this hall several times. Materials are always very important, and my personal interest when I met Professor Ilyas about 10 years ago, I was so impressed that this university was a management university and open university in different subjects. But to work and develop the science laboratories is a major task, which I think I must salute Professor Ilyas. It has been my pleasure to come to this hall several times. Today, Professor Asghari's lecture took me some 62 years back when I was a student at Birmingham, and the first time after nuclear training here in Pakistan, first time used the X-ray diffraction Philips equipment. So, but the project for my doctorate was gamma ray diffraction. So, as she has very well explained, the condition of diffraction is the wavelength should be corresponding to the lattice parameter of the crystal you are investigating. So in nuclear physics, we have certain gamma rays which are of the order of few keV. Usually, as the question has been put, that the X-ray sources are of a few keV, 10 keV, 12 keV, and we found at the time was the first investigation a gamma ray which is a 14 keV, which is just matching to the lattice constants of various crystals. So this was a very new experiment which was given to me, and alhamdulillah, it's being referred, that work, right up to now, for the last more than 50 years. Because it was the basic investigation. Gamma rays have a very high resolution as compared to the X-rays. And certain investigations in the Bragg law, the scattering of these X-rays with the atoms have certain energy loss also. But that energy loss was too small. That is, inelastic scattering of X-rays was difficult to find out by the resolution available in the X-ray diffraction, which was about 10 to the power 10 keV or so. But these gamma rays had million times better resolution. So small energy changes in the diffraction we could investigate, and that was a first experimentation of Waller's theory of 1923, which was we verified in 1963, something 40 years afterwards. So he was very happy anyway. And that fundamental work is being referred even now. So thank you very much for taking me. I wanted to talk about nanotechnology and its investigation and so on, but this took me back to my, I didn't know that she was going to say explain very well the basics of the X-ray diffraction. But now, as the condition is that the wavelength of the system should be, X-ray should be, or any system should be of the order of the lattice parameters. So there were other radiations, like I mentioned, gamma rays, and later my experience went into neutron diffraction, which at the reactor at Pinstack I was involved in since 1966. So that was there are electron diffraction there. The condition, as she said, should be the wavelength of the particle. In this case, electrons and neutrons should be of the order of the same as lattice parameter. So thank you very much for taking me back to my basics. And now we come to today's of materials. I can't say, but I don't know. In early times, I might have given a lecture at the Qaeda University, I think. Thank you very much. So kind of you. So anyway, today's talk on the materials is a very interesting one, which has taken my last 10 years actively in a new concept of nanotechnology. But as some of the younger ones might know, that the word nanotechnology was first time I expressed in my talk in 1995 at Pinstack. I was interested at the time in new materials at the time, and these names of smart materials, new materials, were actually scientific names coming into the literature. And one of the area was these biomaterials. So at the time, as a solid-state physicist, I tried to get into the new things. And these biomaterials were very popular at the time, your hip joints and, a lot of these medical applications. So while going through the literature, I found there are other types of materials also. And that was the word used by, although the father of nanoscience is considered Feynman, who gave a lecture in 1959 at Caltech and said when the particle sizes become smaller, their properties from the bulk are very different. So this was the concept he gave, and the nano word was occurred from a Japanese in 1974. He was working on silicon transistors, and he was seeing the effect of silver atoms on the base atoms of silicon, and how small these electronic effects are in these transistors. So the silver atoms he was using a very small size, and nano was known to us as a measure of 1/1000th of either time or measurement. So he said, I'm using atoms, silver atoms, to see the effect of silver atoms on the silicon base. So I'm using the nano-sized materials. And since silicon is a technological solar cell, silicon is a technological item, it is nanotechnology. So in his paper, for the first time, he used the word nanotechnology. Although Feynman had given the germs of this small-scale science, At nanoscience, at the atomic level science, the properties are different from the bulk materials of the same material. But the word actually nanotechnology was used by Japanese. So anyway, this is information which I recollect from my early times. Now, coming up then, of course, when the technology was there and the materials were used at very small level, then the name nanomaterials came, and several fashionable names of smart materials, new materials were actually being used in the literature. Now there is a tremendous amount of literature on the nanoparticles of zinc oxide, silver, copper, you name anything, in even polymer materials, the nano-sized materials are being used. So at the time, over the years, I was interested in nanotechnology, giving lectures in early this century, and Professor Ataur Rahman was very keen to appreciate this new technology because it had a lot of industrial applications. I'll come to in a few minutes of the 15 minutes I have survey over for the new people. And he then formed a national commission under the Ministry of Science and Technology in 2005, and I was working for chairman of this honorary basis for 5 years, and we distributed about 900 million rupees to 5 projects out of 10 we got at the time. 200 million to ComSats, about 200 million to NIPJ for medical applications, to Qaid-e-Azam University, magnetic studies to Dr. Hasnan. There was a committee formed, and we investigated about 10 projects, and out of 10 projects, 5 projects were selected based on the experience of the people and what we could think of merit. So that is how this nanotechnology started in this country. But my passion was to give lectures here and abroad. So slowly, because of the compulsion of nanotechnology applications at the world level in industrial, all types of industries, the word also spread by its own, not from myself very much, but from the international literature. And when anybody wanted to go for PhD, this was a small scale applications of the project. So nanotechnology in Pakistan also, in addition to our efforts, spread, and almost now every university, I think, has either chemistry or biology or so. So this is now a nanotechnology spread in research. But what is lacking, I think, is the industrial applications of this technology. The world is making a lot of benefits from the industrial applications. And I was looking up the survey recently, $1 to $2 trillion industry of all nano products are available in the market world over. Trillion, what to talk of $1 million, $1 trillion industry. It's a huge, whether it is the space science or it is a new revolution in medicine under the name nanomedicine, treatment of cancer and treatment of MRI, and a lot of applications. You go to the literature and you will find a lot of applications of this technology. It's a sort of industrial revolution as it properly known as. But unfortunately in Pakistan, our industry has not taken up. Although in my earlier times, in 2011, I got one contract from Canada to investigate industrial applications of nanotechnology in Pakistan and in the region. Region means Sri Lanka and India. And I addressed twice to the Chambers of Commerce of Sialkot, because a lot of applications are in the sports industry, hockeys and lighter and stronger materials and these tennis rackets and even golf balls and, So surgical instruments, their layers with nanomaterials and so on. But twice, 60, 70 people are sitting, very big industries, but somehow they are buying the products, the nano paste, putting into the hockeys and making lighter and selling it, but not using the talent which is available within Pakistan unfortunately. So I think our efforts to our youngsters and our fellow friends must be on convincing this industry somehow we have in the Atomic Energy Commission found one formula to convince the these industrialists. That is, you first do some work to save their money of their products, and then they will come up. I can cite one example, Dr. Khurshid knows. We had a polymer chemist, very communicative and good polymer scientist some 30 years back at Pinstack. He went to Lahore. Atlas company है ना, वो जो powder tire बनाते हैं. So he happened to go there, and he was told that this tons of powder is lying useless because it doesn't work now. He was a researcher. He said, well, he guessed that there is some moisture in the, and he said, give me 1 kilo. He brought 1 kilo powder into the Pinstack and put a vacuum pump and removed the vapor, and it worked. So since that time, वो उसके मुरीद बने हुए हैं. So the crux of the matter is you first do their thing. This is a message for our researchers, like you first do their thing which saves their money, and then they will come into this. This is Pakistan's thinking for industrials, but not like others in other countries, industries, where they spend money for postdocs and doctorate students to give money for industrial applications. Anyway, so nanotechnology happens to be now very common in Pakistani universities, but the lacking, again I repeat that we should try to go into the industry so that we can earn some money. These two industries I proposed to Canada, the textile industry and sports industry, because they were earning money. So I thought, this is 10 years back, 15 years back. So I thought that if neighboring countries compete with us, we will suffer in our exports. And these were the two proposals which we sent to Canada, and they approved it and gave us some money. So anyway, I'm now coming to the new concept of, in the next 5-6 minutes, new concept of helping the nanotechnology flourish in Pakistan and all over. And this is the concept. When you have a technology which is sort of industrial revolution, you need to have properly trained people for that. And this is to get maximum benefit of the well-trained people. So this was a concept that we must have some formal degree in nanotechnology. And I was emeritus after my retirement in 1996 at Pinstack, but Preston University Chancellor was a very visionary, and he approached me in 2009 again about your time, and he said, we are interested in education of the nanotechnology. So there I proposed one course of BS in nanotechnology, and so that we can produce BS graduates who can go to research and into industry applications with well-equipped basic knowledge of practical and theory. So fortunately, I was able to get some professors who are, my concept was retired professors, soon retired professors, and some young people, so that in a certain management, Pinstack was too big for management. I had some experience, but this was a new start, but very challenging one. So I was able to get 6 full professors for this educational program of BS level, retired from Qaeda-e-Azam University and from Atomic Energy Commission. So this was fortunate, and some younger PhDs and MPhils. So we designed a course of BS with 132 credit hours, with nanobiotechnology, with basic physics, quantum physics, based on nano-quantum physics, and so on. So जो former 5th year वाले course होते थे, these people were very experienced. इन्होंने practical और theoretical उस level पे, ताकि बच्चे को BS level पे basics और strong basic at advanced level मिल जाए. Not necessarily one MSc पूरी physics की या chemistry की उस level की 6th year को छोड़ के. तो 4 subject 132 credit hours हमने arrange किए. Physics, chemistry, biology, and material science. This was the only concept and only BS in the whole of Pakistan, and in consonance with some advanced countries. In Germany, in Australia, people were combining the multidisciplinary concept of combining 2 subjects, physics, chemistry, biology, physics, some 3 And only there was one university in Chicago which had 4 subjects at one BS level. So this was a new experiment we started. We didn't know there were some views that what will happen to the employment inside the country. But anyway, in any new things, when you have to venture into it, otherwise the thing will never come. So I thought, well, I was supported by the chancellors and from the Pakistan Academy of Sciences some grants. So alhamdulillah, by now we have very good, well-established laboratories, theoretical, of course, faculty, 6 full professors were nowhere, and very few students. That means 10 to 15 we had every year. So it was just a tuitionary, and the result is just before ending in the next 2 minutes. The result is in the last 10 years, we have produced 65 graduates. From 2014 was the first batch. We started the 2010 at Preston University. 2010, the admissions of this course and so on. And in 10 years' time, we produced about 65 graduates of this type, multidisciplinary, 4 subjects at BS level. The advantage is that in between, I had some MOU with China, and there are 30 students with fully funded scholarships doing PhDs. Some have done PhDs in the best laboratories of Chinese Academy of Sciences in Beijing, Nano Center. So we had 5 years MOU first with them, and they gave us 3. Actually, the team of these scientists came and in 2012 and in the Academy of Sciences in Pakistan, and the president was known to me, and he came to Chunli Bai. So the director of this nano center in Beijing was invited to my institute, and I started getting something out of it. And by correspondence, he agreed to give 3 PhDs scholarships every year, fully funded. So I was happy, and the first batch, which came in 2014, I sent 3 best students out of these 15 which passed. And for 5 years, every year 3 students were going on. 30 students are by now, and 3 have done PhDs, one with 19 publications during PhD, another with 16 publications, and the third one also with 16 publications in high impact factor material journal. The advantage is that this base of 4 years is a very new concept, but maybe not very popular in Pakistan for the employment as a lecturer and so on in colleges. But internationally, it's very much accepted. This is I'm talking now as a result of the documentation which I have with me. 65 graduates, 30 in China, and in 11 other countries, fully funded scholarships. MS leading to PhD in the United States, Australia, Japan, because the 4 subjects training is not available even internationally, very common. And therefore, these students are taken. Somebody is doing cancer research, somebody is doing brain research using nanotechnology, somebody is using solar cells. So because the variety of these biological and these 4 sciences are available to these BS4 students. And the total amount which they have earned as scholarship is something like 430 million rupees, 43 crore rupees. So HEC deti hai. So I'm happy that this our journey of 10 years is also like you contributed something to Pakistan's new technology. तो मेरी रिक्वेस्ट अब आप लोगों से ये होगी कि इंडस्ट्री को किसी तरह पकड़ें ताकि दिस टेक्नोलॉजी इज़ यूजफुल फॉर पाकिस्तान आल्सो फॉर इंडस्ट्रियल. तो अगर कोई जनरल किस्म की चीज़ें बातें तो चलती रहती हैं लॉन्ग टाइम, बट आई वुड लाइक टू एंड pay my thanks to Zafar Ilyas to give me time to express to particularly young people if they have certain questions, and I will be happy to give comments, whatever experience we have. It's all for young people. Thank you.
So, sir, thank you for again a very motivation from you about how we can help the industry with our knowledge. Generally, we don't have that kind of a bridge. I think that bridge is missing. So, do you think there is a lack of that bridge if universities can develop a regular visit of the students of the MS and PhD to the industries, like you mentioned in Sialkot, that in Lahore you said about that polymer material that was having a moisture in it. So because we don't have that kind of visit of our students to the different industries, textile industry and rubber industry, steel industry, there are a lot of other industries, and in Karachi as well, and in different cities. So because you have been as the head of that commission of nanotechnology, so because I don't see any kind of that platform, even in the universities, that bring the students regularly going to the industries so that they can interact in the future as well. They can understand the problems what the industry are facing. So maybe any faculty member or any student, they can get an idea, okay, how we can contribute. Because right now most of us, I'm not sure about, I'm not saying everybody, most of us, they are blank about what is happening right in the industry in Pakistan. What are the challenges being faced by the industry? Because mostly, as you said, the raw material is being imported. Because once I remember, you came in Faisalabad Chamber of Commerce about that nanotechnology commission, and they said we don't need to take help from the university. We can buy very cheap raw material from China, and we can go for our textile dyes and the other our fabric.
This is a very important discussion which we have been doing for a long time. Way back in, I think, Atar Rahman, when he was the minister, we organized applications of physics in industry, a conference in Karachi. So I was personally asking the industrialists, please send your technician for a week. And the answer was that, if he goes for a week, our production will suffer. So they did not realize that the training you will get will save a lot of money in improving the products. ये concept वहाँ पे अभी तक नहीं था. तो मेरे ख्याल में अब ये आपका point जो है ना, एक internship का BS level पे है 6 weeks. So what we did, since I was involved in this concept of industrial applications of nanotechnology, I sent my 2 students to Sialkot industry for 6 weeks. And they, told them that you make this sort of this sort of paste and, surface modification of the surgical instruments. And one of the industry adopted this coating of their surgical instruments. And they wrote me that, this is 7-8 years back, they wrote me they have increased about 13% of their products in export industry. So by the improvement of nano coating of the surgical units. But on a mass scale, this was only a small amount, but on a mass scale, the industry is not coming up. I heard that from Munich, there is a hockey exporting company in Sialkot. They are importing the paste, nano paste from Munich, somewhere, industry. Hockey, they have a plastic empty. How do they make a hockey? It's a plastic envelope of the hockey shape, and they put this resin, imported resin into it, and temperature and so on, and the hockey. They gave me one hockey written as nano hockey. Nano hockey. So I've got it about 10 years back. I think they gave me one copy. So nano hockey, they are selling it from. They can make the paste material here from our chemists and so on. So unfortunately, they have to be. But one thing we tried, as I said, you save their money, and then they will come up. So I think let's continue interaction with them. The experience of British industry was that at the university they had in a syndicate one member from the industry as a member. That was an old concept. In Germany, there was a new concept coming up some 15 years back. The research professors opened a small private company, and they were interacting. They knew what Steinbeis Foundation was the name. I was working just literature-wise. And that group of professors went to the industry and the problem of the people. For example, वो एक चिमनीज का प्रॉब्लम था, वहाँ पे गैस जब निकलती है, तो that is more than that. And they knew that such and such a university has the experience of doing this. And so this in between, and that is now flourishing international company. So there have been different models, but in Pakistan is a difficult model that you go to them and save their money and then they will come. This is our experience. Please.
یہاں پاکستان میں انڈسٹری میں وہ کمپنی بھی اپنی کمپنی کو لانچ کرنا چاہے تو انڈسٹری کو فالو نہیں کرتی. یہ بھی ہمارے یہاں کچھ بنے انڈسٹری میں بزنس انفارمیشن سینٹر کے نام پہ. لیکن ان سے کبھی بات کریں تو وہ کہتے ہیں کہ فیکلٹی ممبر وہ کان وہ اینی ادر جاب یا آپ کسی اور کمپنی میں کسی کنسلٹنسی بھی لے سکتے ہیں.
یہ اس کا امریکن ایکسپیرینس اس کا یہ ہے کہ دیز ریسرچرس دے لیو دا جاب آفٹر سم ٹائم when they and they open the company and is very successful. Even in nuclear equipment, I know some of the Oak Ridge people, American scientists, way back in 25, 30 years back, they're very good scientists, researchers. And then they left the job and opened their company for nuclear instruments, and they earned a lot of it, and the companies are coming up in a big way. So I think, but one thing important in application, our experience is that unless you have a R&D experience of say 10 years, a good experience, you cannot make the product which is compatible with the international market. And our experience from the atomic energy was, we have made certain things. R&D was for materials, for example, these reactor tubes of zirconium, a lot of things. But those people who had experience of R&D, they produced compatible and good quality products. یہ کانسیپٹ کہ آتے ہی ایک نے پی ایچ ڈی کیا اس کو پروجیکٹ دے دیں وہ ایک تو ویسٹیج آف ٹائم ہوگا, ویسٹیج آف منی ہوگا, ویسٹیج آف کوالٹی ہوگی. سو آئی تھنک فرسٹ یہ جو پیپر چھاپنے ہیں یہ بھی فائدہ مند ہے. فرسٹ دس از آور کانسیپٹ. آئی تھنک باہر بھی یہی ہے, باہر کے ملکوں میں جو ترقی کرتے ہیں کہ آر اینڈ ڈی اسٹرانگ ہونی چاہیے, اس کے بعد آپ انڈسٹری میں ضرور آئیں کیونکہ کنٹری کو فائدہ کیا آپ پیپر چھاپنے کے آل یور لائف یورس. ٹھیک ہے, اٹس ون سیکشن آف اٹ از اوکے جو کہ آپ بریک تھروز کر لیتے ہیں وہ تو کرتے رہیں, لیکن عام جو اچھا ایکسپیریمنٹل ریسرچر ہے اسے انڈسٹری میں آ کے تو ہیلپ ہونی چاہیے. لیکن یہ ہے کہ وہ اس طرح ریزائن کر کے پھر کیا کرے گا یہاں پہ نوکری شوکری. تو ان بٹوین سم سلوشن ہیز ٹو بی کہ ایڈوائزرز ہوں وہ انڈسٹری کو اور باقی پروفیسرز ہوں اور اس طرح پروجیکٹ پی ایچ ڈی ریسرچ کے لیتے رہے انڈسٹری سے. اور یہ ماڈل یو کے میں چل رہا تھا, اب یو کے ذرا کمرشل ہو گئے ہیں, لیکن دس واز اے ورکنگ پروفیسر واز انوالوڈ ان دی انڈسٹری ٹیکنگ دیئر ریسرچ, اینڈ دیٹس ون تھنگ وچ آئی تھنک وی کین ٹرائی. اٹس اپ ٹو یو. ہم نے تو جو تھوڑا بہت کرنا تھا کر لیا اپنی طرف سے, بٹ دیر از لاٹ آف ہوپ, دیر از اے لاٹ آف ٹیلنٹ. پاکستان کا ٹیلنٹ تو آئی ہیو سین مائی سیلف. ایک اور بہت سی چیزیں ہیں, نوبل لاریٹس میٹنگز ہوتی ہے جرمنی میں, کوئی 30-35 نوبل لاریٹس ان فزکس سے ایک ہفتے کے لیے اکٹھے ہوتے ہیں ہر سال, ایک سال کیمسٹری اور بایولوجی جس میں مٹیریل سائنسز میڈیسن میں. تو اس میں 1951 سے وہ ایک ہفتے کا یہ کر رہے ہیں. از اے ریئر کورس. اس میں پاکستانی اسٹوڈنٹس میں نے انٹروڈیوس کیے تھے, اینڈ ایچ ای سی از ناؤ سپورٹنگ سنس 2003. Every year we are sending 5 to 10 good students in these fields. اور بڑا انسپائرنگ. وہاں پہ دیکھا ہے کہ کوئی 60-70 کنٹریز کے لوگ آتے ہیں, اباؤٹ 500 بیسٹ اسٹوڈنٹس. تو پاکستانی انٹریکشن بڑا اچھا ہے. اور 4-5 سال کی میرٹ کے اسٹوڈنٹس کے بعد انہوں نے اس آرگنائزیشن نے جرمنی نے ہمیں لکھا کہ ہم MOU کرنا چاہتے ہیں. ویری فیو کنٹریز آر فارمل ممبرس اینڈ پاکستان ناؤ از اے فارمل ممبر آف اٹ, اور HEC سپورٹنگ دس فلی فنڈیڈ. تو پاکستان میں کہنے کا مطلب یہ ہے کہ ینگ ٹیلنٹ بہت ہے, اس کو یوز کرنے کا آن میرٹ از این امپورٹنٹ میٹر. تو باتیں بہت سی ہیں, آئی ووڈ لائک ٹو انٹر کیونکہ آپ نے اور کام بھی کرنے. تھینک یو ویری مچ. اینڈ چائے پہ یا جب بھی کوئی ڈسکشن ہے تو وی آر ریڈی فار اٹ. تھینکس ویری مچ.
Thank you very much, sir. Now, let me call upon an independent think tank professional, an expert nuclear knowledge management, peaceful uses of nuclear techniques and SDGs, an expert in nuclear energy, expert in project planning, development, management and evaluation, an expert from Pakistan Atomic Energy Commission who has served there for 39 years in a variety of capacities and is currently a distinguished visiting fellow at the Center of International Strategic Studies in Islamabad, Sir Sayyid Javed Khurshid. Sir, please.
So instead of giving a lecture here, I just wanted to talk and say a few words about Dr. Zafar Ilyas. There are few things which are already mentioned by NM Butt, لیکن صحیح تاثرات میرا خیال ہے کہ میں اردو میں بولوں تو وہ دل سے نکلتے ہیں. ظفر اقبال صاحب کے آنر میں آج کا فنکشن کہنا چاہیے, بیکاز ہی سیڈ آئی ایم ریٹائرنگ. آئی ڈونٹ ایگری ود دس ورڈ, اینڈ اسپیشلی فار دا سائنٹسٹ, because I retired in 2011 and I am doing much better work after the retirement. And as you has asked many questions, and I have the answer now for those questions. کیونکہ اس زمانے میں تو آپ اتنا انوالو ہوتے ہیں چیزوں میں اور انہیں مکمل کرنا چاہتے ہیں, آپ اس پالیسی میٹرز اور یہ چیزیں جو ہیں کور نہیں کر سکتے, اور آپ کا ویژن بھی نہیں ہوتا اتنا اس وقت, میرا خیال ہے, کیونکہ آپ کو ٹائم نہیں ملتا. جب آپ کا ویژن ہوتا ہے, آپ کو ٹائم ملتا ہے, آپ بہت چیزوں کے ساتھ جا کے دیکھتے ہیں ان کو اور گہرائی سے, اور آپ کا تھنکنگ کا جو اسٹائل ہے وہ بالکل چینج ہو چکا ہوتا ہے. اسی لیے میں چاہتا ہوں ایک لفظ کہنا یونیورسٹیز کے لیے بھی اور سب کے لیے, کہ تھنک ٹینکس ہونے اسینشل ہیں آپ کے ساتھ, کیونکہ وہ جو تجربہ دیتے ہیں پچھلے 40-50 سال کا ہوتا ہے, اور اس کے مطابق وہ اس کو کہتے ہیں. آج مثلاً 2 تجربات کا ذکر کیا NM بٹ صاحب نے. میں ان کے ساتھ 1987 میں پہلے پروجیکٹ میں شامل ہوا, جو پاکستان کا پہلا پروجیکٹ تھا. وی ہیڈ اے کمیٹی آف 4 پیپل, اور وہ تھا ریڈیشن اسٹرلائزیشن آف دا سنگل یوز میڈیکل پروڈکٹس اور پولیمرائزیشن. تو پاکستان میں جب ہم نے وہ پروجیکٹ انٹروڈیوس کیا, لاہور میں ہم نے جگہ لی, پہلا پروجیکٹ تھا, اور AIOU کی 3 کانفرنسز تھیں. میں چاہتا تھا ٹیکنیکل لوگ آئیں, کیونکہ سیکرٹری کے طور پہ میں کام کر رہا تھا, اینڈ ہی واز دا چیئرمین آف دیٹ پروجیکٹ. آپ یقین کریں کہ کوئی ایک انڈسٹریلسٹ نے اپنا بندہ نہیں بھیجا. ہم ان کے پاس گئے, ہم نے یہاں تک کہا کہ 3 دن کے ہم پیسے دیں گے, اور AIOU کے سارے لوگ آئے ہوئے تھے, UN سے ممبرز آئے ہوئے تھے. انہوں نے کہا نہیں جی, ہماری پروڈکٹ 3 دن ہم کیا کریں گے بیٹھے ہوئے. پھر ہم نے یہ بھی کہا کہ ان لوگوں کو ہم پیسے دے دیں گے, اسکالرشپ ٹائپ کی چیز دیں گے 3 دن کے لیے بھی, تب بھی بھیجنے کو تیار نہیں تھے. پھر ہم نے ان سے یہ کہا کہ آپ کی پروڈکٹ کا ہم ریڈیشن کر کے 50% چارجز نہیں کریں گے کچھ عرصے کے لیے, تو آپ بھیج دیں. اور یہ پاکستان میں پہلی دفعہ شروع ہو رہا تھا. یعنی جتنی میڈیکل پروڈکٹس آتی ہیں, سرنجز وغیرہ, یہ وہ سب کو اسٹرلائز کر کے, سنگل یوز اسٹرلائزیشن ہے, یعنی پیکٹ کے بعد, لیکن کسی نے نہیں بھیجا. تو یہ صورتحال ہے انڈسٹری اور سائنٹسٹ کے میلاپ کی. تو یہ بہت ضروری ہے سب سے پہلے کہ انڈسٹری سے ہمارے پاس پروجیکٹ آئیں اور ہم وہ پروجیکٹ ان کو کر کے دیں. اس میں چاہے ان کو پیسوں کے لیے بھی انوالو کرنا ضروری ہے, کیونکہ بغیر پیسوں کے وہ نہیں آئیں گے. اور بٹ صاحب نے اس کا جواب دیا, ان کو چیزیں چیپ مل جاتی ہیں یہاں کے علاوہ. تو یہ ایکسپیرینس ایک میں آپ کے ساتھ بیان کر دوں. دوسرے, ایک زمانے میں جب میں یونیورسٹی میں پڑھا کرتا تھا, تو یونیورسٹی میں باقاعدہ انڈسٹریل ٹرپس ہوتے تھے, اور وہ ان چیزوں کو وزٹ کرتے تھے. اور میں اپنا پہلا زمانہ بتاؤں, میں نے داؤد خیل انڈسٹری پہلی دفعہ لگی تھی, جس میں کہ فارمیسی کی انڈسٹری بھی تھی اور دوسری سیمنٹ انڈسٹری تھی, فرٹیلائزر انڈسٹری تھی, وہ وزٹ کیا. ہمارے یہاں کہاں گیا وہ ماحول یونیورسٹیز میں؟ یہ آپ کا جواب ہے کہ لوگ جب تک اسٹوڈنٹ لیول پہ ان کے ساتھ جوائن نہیں ہوں گے, پروجیکٹ نہیں کریں گے, ان کو فائدہ نہیں پہنچے گا, ہمارے انڈسٹریلسٹ سامنے آنے والے نہیں ہیں. یہ تجربہ ہے 40-50 سال کا, اور آپ کے چیزوں کے جو سوالات آپ نے کیے ان کا جواب ہے. تو اٹ نیڈز اے لاٹ آف تھنکنگ ایٹ دا بیک گراؤنڈ. اس کے بغیر نہیں ہوگا, چاہے کوئی بھی فیلڈ ہو, کوئی بھی ٹاپک ہو. بیکاز آئی نو کہ سائل کوٹ میں اس وقت 2 انڈسٹریز کے ساتھ ایز اے تھنک ٹینک کام کر رہا ہوں, جو یہاں سے لیزرز کے وہ کمبائن کر کے میڈیکل یوز کے لیے بھیج رہے ہیں. اب کتنا سائنٹسٹ اس میں انوالو ہو سکتا ہے, وہاں ایک جاہل آدمی اس کو کنٹرول کر رہا ہے. ٹھیک ہے, تو یہ ایک بہت بڑا مسئلہ ہے جو بہت تھنکنگ چاہتا ہے سب کچھ. آخر میں اپنا ختم کرتا ہوں یہاں کہہ کے کہ ظفر الیاس صاحب سے میری 2009 میں ملاقات ہوئی, جب ہی واز کمنگ ٹو اسلام آباد اینڈ وانٹیڈ ٹو گیو ہز ایکسپیرینسز, ٹیچنگ ایکسپیرینسز ٹو دا اسلام آباد ایریا. پھر انہوں نے, میں اس وقت اٹامک انرجی کمیشن میں ڈی جی پروجیکٹس ہوتا تھا, تو ان سے ملاقات ہوئی اور یہ بات چلی. پھر انہوں نے علامہ اقبال جوائن کر لیا. اور جو بات ہے وہ یہ ہے کہ آدمی اپنے زمانے میں جس وقت وہ جاب میں ہوتا ہے بہت کام کرتا ہے, لیکن میرا خیال ہے اس کی زیادہ ضرورت جاب کے بعد ہوتی ہے. اور وہ جاب کے بعد ایک سائنٹسٹ جو ہے نا وہ ریٹائر کے بعد فارغ نہیں ہوتا, بیکاز ہی اسٹارٹ تھنکنگ. بیکاز سی آئی ایم ریٹائرڈ فار سو مینی ایئرس, but I am now a policy maker. I am a thinker. I am now advisor to 4-5 industries. I am working for, I am delivering lectures to 3 universities, and I am working on those topics which very few people are working in Pakistan. I am working on weapon of mass destructions like chemical weapon controls, biological weapon controls, and now my topic is nuclear energy, climate change, which is very near to the problems we have. So آدمی ریٹائر نہیں ہوتا, خاص طور پہ ایک سائنٹسٹ ریٹائر نہیں ہوتا. تو یہ میں ان کی بات ذرا سا سپورٹ نہیں کروں گا, اور ان کو کہوں گا کہ اس زیادہ اور زیادہ محنت سے آگے کام کریں, اور جو انہوں نے کام کیا ہے وہ قابل ستائش ہے, اور ہمیں ان کو ایک کلیپ دینا چاہیے جو بھی ان کے. تھینک یو سو مچ.